This is a continuation of the video notes on 1.2 forces. It ended rather abruptly in the middle of terminal velocity last time, so this one is just going to finish off the section on terminal velocity. So you'll remember that we were thinking of a body free falling from a high height. And if you look at the very first diagram, which you will have had from the last note, you can see that it's just been released. So the only force on it at the moment is its weight. It's not built up enough speed to have any drag yet, so it's accelerating at g. That's when it's just released. The middle diagram is a little bit later on, and by this stage the body has been falling for some time, so it's built up some speed. The weight, of course, is exactly as it was before, mg, but now that it's built up some speed, it's also built up some drag, because as you know, the drag force increases with the square of the speed. You double the speed and you quadruple the drag. So drag force is built up a bit now. So it's still accelerating, but the acceleration is now a bit less than g. And there's the free body diagram for it. Now eventually, if it falls for long enough, the drag will continue increasing until it reaches its limit. And its upper limit is that it can't get any bigger than the weight itself, so it equals mg. Now when you get to that point, the drag equals the weight in magnitude, and so the forces are balanced eventually, and therefore there's zero acceleration, and the body is falling downwards with a constant velocity. And that constant velocity is called the terminal velocity, v subscript t. Should just remind you that this is the ground. Okay, so that's the terminal velocity, and you did meet that at National 5. If we then plot a graph of that terminal velocity against time, well, I'm imagining a parachutist here who jumps out of a plane, and initially he doesn't have his parachute open. So at the beginning of the graph, he accelerates more or less with a uniform acceleration at g, but as the speed increases and the drag increases, he's still falling downwards with a downwards velocity, but the rate of increase of that velocity gets smaller, and eventually the rate gets to 0. That's the rate of increase of velocity, and he's actually now travelling at the terminal velocity. So that's with no parachute. Okay, so there's his terminal velocity, no parachute. So if he begins at point A, he reaches a terminal velocity at roughly at point B, and he continues to point C. If at this point, point C, he opens the parachute, then he suddenly experiences a huge upwards drag force, much bigger than his weight. So there is a rapid deceleration, and he does this. But as he slows down, the drag force gets less and less, till eventually the drag force comes right down so that it equals his weight again, and he reaches a new terminal velocity. So at this point, we'll call it point D, he has reached a new lower terminal velocity. Parachute obviously open. I mean, typically for a parachute, the terminal velocity of the parachutist might be perhaps 2 meters per second, something of that nature. Whereas when we're up at the top end of things, gosh, we're talking there at maybe 40 meters per second or thereabouts. Okay, something really quite fast. So that is terminal velocity.